I guess I'll start the talk first with a very brief self-introduction. My name is Yiyun Liu, and I'm a PhD student at the University of Pennsylvania. My advisor is Professor Stephanie Weirich, who's also a co-author of the paper. So first, what is this talk about? In a general-purpose programming language, dependent types help us write safer programs. But unfortunately, evaluating proofs at runtime is both costly and sometimes hard to avoid. Erasing proofs, which are encoded as programs, is dangerous when those programs are allowed to be partial. And this is what motivates us to design this core calculus called systemd, which is dependently typed, and it supports both partial programs and erasable proofs. And most importantly, it is based on the design of GHC's core intermediate language, which makes it suitable for future extension of the Haskell programming language with dependent types. For the upcoming examples, I'm going to adopt the syntax from the dependent Haskell proposal, which is not yet implemented in GHC. As an alternative, I could have used the singletons library to present all the examples, but it's nice to assume full dependent types so we get a cleaner syntax to formulate the problem. So first, why do we need dependent types for a general purpose program language? Here's an example that most people are familiar with. It's the length index vector type. It is the same as a list type, except it's additionally indexed by a unary natural number, which tells us about the size or the number of elements stored inside the vector. The length index is very useful because it allows us to specify more precise type signatures for our functions. For example, we can define this function called vhead, which takes the first element from the list. And by constraining the input to be a vector of a non-zero size, which ensure that we never accidentally apply vhead to an empty vector. And for those of you who already know Haskell, this for all keyword, I'm pretty sure you have seen it already. But in dependent Haskell, for all is more general. It introduces a dependent function type, but it also means that the argument is erasable. And in this case, we're allowed to use the for all keyword to quantify over the length index n and the type variable a, because neither is used in the body of vhead. We can also use dependent types to reason about program equivalence through the equality type, which I present here as a generalized algebraic data type. So one program that we might want to reason about is the plus operation for unary natural numbers. And a simple yet non-trivial property is that for all natural numbers m plus c is equal to m. This property is not immediately obvious to the type checker because plus is defined by a pattern matching over its first argument. And in this case, because m is a variable, the computation is blocked. To prove this property mathematically, we would need some sort of inductive reasoning. And this would correspond, it can be encoded as a program that is recursive. So the @nz function has a pretty self-explanatory type signature. It encodes the exact property we want to prove. The for each keyword serves a similar purpose as the for all keyword. It introduces a dependent function type. But here, unlike for all keyword, for each means the argument is not erased at runtime. And in this case, the argument n is not erasable because @nz uses it by doing a case analysis over it. To show you how this recursive function corresponds to an inductive mathematical proof, I listed the proof obligations on the right. In the base case, we need to show 0 plus 0 is equal to 0, which is a trivial reflexivity proof. In the inductive case, we start off with our initial goal. We do a few steps of reasoning through reduction and congruence, and we end up with the goal that n plus z is equal to n. And that is exactly our inductive hypothesis. And this corresponds to, in the function, as a recursive call @nz of n. And in order to make this hypothesis available to the type checker, we do a case analysis over @nz of n. And within the body of the pattern match, the only thing we need to do is to write down REFL, and the type checker will automatically pick up the inductive hypothesis and apply reduction and congruence to come up with a proof. You don't need to explicitly supply a motive. It's very concise. It might be reminiscent of SMT-based theorem provers if you're familiar with those tools, though the underlying mechanism is different. We usually don't think of @nz as function, but rather as a witness of a property about our program. But it's worth keeping in mind that if we were ever to evaluate this function, it's going to take time that's linear to its input because of the recursive call we made in the successor case. And we'll come back to this later. So far, it seems that we have digressed a little by talking about theorem proving instead of programming. But it turns out if you want to leverage dependent types, you inevitably have to write proofs. And here's an example. Consider the function v_append. I'm going to omit its definition, but what it does is take in two vectors and append them, concatenate them together. The function we want to write is this append nil function, which takes an input vector xs of size n and append it to an empty vector. It's a rather roundabout way to define an identity function for the vector type. Because if you append a vector to something that's empty, you end up with the same vector. So we would expect the return type to be the same as the input type, a vector of size n. But unfortunately, this append nil function written as the way it is won't type check, because if we follow the type signature of v_append exactly, the body of the function is a vector of size n plus z. And for the same reason we mentioned earlier, the type checker doesn't know that vector of size n plus z is the same as a vector of size n. In order to fix this program, we can reuse the proof @nz we have written earlier. By doing a case analysis over it, we can teach the type checker that this program has the right type. And in order to do so, we first explicitly quantify the length index with a for each keyword, so we can refer to it explicitly in the body of the function's definition. And through a case analysis over @nz of n, now it knows that a vector of size n is the same as a vector of size n plus 0, and our program type checks. So one thing that really sets programming apart from theorem proving is that we really care about the computational cost. So how does our previous append nil function perform? Here's the program we wanted to write initially. And in order to convince the type checker that our program is correct, we need to add a case analysis at the front. And every time we apply this function, before we get down to the real action, which is appending the vector, we need to first evaluate the proof @nz of n. And for the reason we discussed earlier, the pattern match is going to add runtime cost that is linear to the size of the vector. And that is not ideal. So just to be fair, append nil is not a useful function. I personally would never write it in practice. But we can still draw a comparison between append nil and its counterpart when we are dealing with when we are writing the same function for the plain list without the length index. So by using dependent types, we write safer programs, but now we have this unnecessary performance cost. And in fact, there's more practical programs you can write in practice, and you would run into the same issue with proof evaluation. And this has been observed in the development of the Crucible symbolic execution framework, which is implemented using Haskell with the dependently typed features, or I guess the fancy type features. So if proofs get in the way of performance, why don't we just erase them? And in fact, if we stare at the definition of the @nz proof long enough, we might feel very entitled to do so. Because in both the zero and successor case, we end up returning reflexivity regardless. And if n is a natural number, not diverging computation, then @nz of n should just evaluate the REFL. And it seems a little pointless to burn some CPU cycles just for sake of the computation whose result you already know beforehand. But it's worth keeping in mind that we work in a program language, which means your equality proof could look like something like this. You use a loop as a witness for two unrelated types A and B. And by doing a case analysis over this proof, this bogus proof, you can write this coerce function that takes an input x of type A and casts it to something of type B. Just from the signature alone, coerce is pretty scary but it turns out to be rather harmless because if you ever try to run it, you're going to get stuck in the infinite loop. It doesn't do anything useful, but it doesn't crash. However, if we try to erase the pattern match from our program, we end up with this actually scary definition of coerce, which behaves semantically the same as an identity function, but is able to cast a term x of type A to another arbitrary type. And if you don't use this function without with any caution, you can easily write a program that crashes. Here's sort of a recap of the problem that we're really trying to solve. Features such as general recursion are essential for programming. But now that we can have partial programs witnessing equality types, the equality proofs can no longer be safely erased because they could very well be bogus. And it might be possible to impose termination checking on our programs, but it's not very practical because it takes away the useful programming features that we really need. Here's an important observation. If our program language is able to differentiate between partial and total computations, then maybe we can at least erase the proof terms written in sort of the sublanguage that is known to terminate. To capture the essence of the problem, we designed this calculus called system DE, which is a dependently typed system that tracks termination and relevance through modalities. Terms in this language are split into two fragments. A term could either be programmatic, it's allowed to use arbitrary features like general recursion, and it may diverge. The term could also be logical, and it uses a subset of the programming features, and they are subject to termination checking. It's worth pointing out that modalities here don't implement termination checking. They merely tell us on which fragment of the language termination checking should be applied. Our goal here is to allow programmers to write non-trivial proofs in the logical fragment, and we can use these proofs in either one of the fragments, and they induce no runtime cost. The typing judgment in our new model type system is indexed by a modality which tells us which fragment the term belongs to. When it's L, the term is logical. When it's P, the program is programmatic and may diverge. Function types are now indexed with a modality as well, which tells us whether the function takes a logical input or takes a programmatic input. So using modalities to distinguish between total and partial computations is not something new, and our work is more or less inspired by the zombie trellis program language. However, I also want to point out that being able to tell partial and the total computations apart also can be found in existing languages such as Idris and Agda. You can use pragmas to specify each individual functions as either total or partial. Though through modalities, it's slightly more fine-grained, which we kind of discussed the details in the paper. Here's a very important convention. When modes are dropped from our notation, we assume that the term or the input argument is programmatic. For example, A arrow B means it's a function from a programmatic, takes programmatic input and produces a programmatic or potentially diverging output. Here's an example of how termination checking with modalities works in our language. First, let's look at the familiar definition of the factorial function. So without modalities, it's apparently a function from net to net. With modalities, we can assign fact to be a function that takes a programmatic net as input and produces a programmatic net as an output. This corresponds to not imposing any termination checking at all. We don't enforce termination checking at the call size of the function either. And in fact, all existing Haskell programs from net to net can be assigned this type signature. And assuming that our underlying mechanism for termination checking knows about structural recursion, we can also assign fact to be a function that takes a terminating or logical input and returns a logical number as an output. However, regardless of the underlying mechanism we use for termination checking, we can never type fact as a function that takes a programmatic natural number as an input and returns a logical natural number as an output, because in general, when we are pattern matching over a potentially diverging computation, the entire computation would also diverge. And our type system with modalities prevents the information flow from the programmatic fragment to the logical fragment, so we don't have an accidental leakage of non-termination in the logical fragment. In system, the equality type is a primitive type, unlike the equality type we have seen earlier, which is defined as a data type. In system, the equality is a primitive. So we use the reflexivity keyword for constructing an equality proof, and we use the reflect keyword to consume it. There's some similarities in terms of syntax compared to the equality type we have seen earlier. The REFL constructor now becomes the reflexivity keyword, and the case analysis now corresponds to the reflect construct. The similarity is good because it means our system is not more, it doesn't demand more from the type inferencer. It behaves very similarly to what we already have. With modalities added to the system, reflect additionally requires the reflected equality to be logical, which is why in the definition or in the signature of safe coerce, the input equality is annotated with the modality L. And in terms of semantics, reflect eq behaves more like a type annotation. This makes it different from case analysis because the reflected equality proof is never evaluated. This new primitive equality type works really well with runtime erasure. And by revisiting the append nil example from earlier, we see how it helps us address the performance issues. So the proof at NZ from earlier with modalities, we can assign it a more precise type signature. It takes a logical natural number as input and returns a terminating proof. Here's the original definition of append nil that uses case analysis, and here's the new version that uses reflect. The most interesting difference can be observed just by looking at the signatures of these two different versions of append nil. In the original version, append nil, the length index n is quantified by the for each keyword. And just as a reminder, for each keyword indicates the argument is not erased at runtime. This is because the length index n needs to be present at runtime in order to evaluate the proof at nz of n, which is a scrutiny of the case analysis. However, with the reflect keyword, since the reflected proof is never evaluated, we don't actually need the length index n at runtime, which means the length index n is now erasable, and we can use for all keyword to quantify over it, which tells us that the length index n is irrelevant at runtime. So this new version of append nil on the right, after erasure, we get rid of the actual length index argument and also get rid of the reflect construct completely. This gives us a version of append nil which behaves, which has the same cost as the append nil for its list counterpart, where the length index is completely erased. And that kind of solves the problem that we wanted to address at the beginning. So far, I have presented the examples using a very declarative syntax, but the reality is system D is actually a core calculus, which is annotated. It is inspired by system D, which is a dependently typed extension of GHC's core calculus. So just as a short introduction of how GHC works, you take the surface Haskell syntax and then elaborate into the intermediate core language, which has properties such as decidable type checking. The conversion rule in system D requires an explicit proof witness called coercions, which I'm going to explain shortly. And we mechanized the type soundness proof of system D in the Coq proof assistant. We proved the preservation and progress. So the reflect construct we were seeing earlier kind of suggests that our equality is really extensionally flavored, which means we need to first show the weak normalization of the logical fragment, so we can prove that definitional equality in this language is confluent. And we need to prove that before we can even show progress. The proof technique is pretty conventional, and the main difficult part is really the definition, because when we are specifying the semantics of the language, we need to be explicit of how we shuffle these explicit coercion proofs around. And also, when we define the logical relation itself, we need to be very careful what it means for something, for a term to be of value when we can have these coercions floating around. So here's how the coercion proofs appear in the conversion rule of system DE. And I'll omit the modalities for now because it doesn't help with the discussion. So if you have seen the conversion rule for other type systems like Martin-Löf's type theory, you'll notice that the judgmental equality for system DE is indexed by this gamma, which stands for a coercion proof. The coercion proof gamma also has to appear in the term syntax every time we apply the conversion rule. Intuitively, you can view gamma as an explicit record of a reduction and the congruence rules that needs to be applied in order to equate A and B. Inferring such a gamma is generally undecidable, but to validate the correctness of the gamma is indeed decidable. Coercion proofs only exist so type checking is decidable. They are completely erasable from the language, which is justified by the lockstep simulation lemma that says if A steps to B, then after getting rid of all the coercion objects, A still steps to B using the untyped reduction relation. And this is a lockstep simulation. So one step prior to erasure, one step after erasure. In order to extend system D, to extend the language with coercions, with the logical equality reflection feature we have seen earlier, we add two new constructs to our language. First, we have this reify construct that takes a coercion object and embeds it as a logical equality proof term. And reflect goes in the opposite direction. It takes a logical term witnessing an equality and gives us back a coercion. So just to see how the surface syntax from earlier corresponds to the actual syntax of system DE, let's revisit the at NZ proof. In the zero case, reflexivity gets expanded into an explicit reduction sequence from 0 plus 0 to 0. And in the successor case, reflexivity gets expanded into two coercion objects, gamma 1 and gamma 2. And you don't need to know the details, but gamma 1 does one-step reduction, gamma 2 applies the congruence rule for application. And the reflect keyword simply makes the at NZ of M proof available as a lemma when we are constructing the coercion proofs, gamma 1 and gamma 2. As the final example, we see how append nil gets elaborated into a system DE. So the most important part about this elaboration process I'm showing here is that the reflected at NZ of M proof now appears inside the coercion object, gamma 1, which is used to cast via append excess nil to the right type from vector of size n plus c to a vector of size n. However, because of the simulation lemma we have seen earlier, the coercion object can be completely erased, which is why earlier I said reflect in the surface syntax, even though it looks pretty much like a case analysis, it's really more like a type annotation because we never actually have to evaluate the proof object when we are running our program. So just to be clear, this elaboration process is not mechanized, it's not formalized either, but it's only here just to show you intuitively that in terms of the elaboration process, we aren't really demand much from the type checker. It's a very similar process as how you would elaborate case analysis and like the original equality type with raffle and case analysis. So I guess that concludes the proof. That concludes the talk. System DE is a dependently typed system that tracks relevance and termination with modalities. The programmers can write erasable proofs in this language, and they can still use all the general purpose program features such as general recursion within the programmatic fragment. The design is based on GHC's core calculus and can be potentially used for the future extension of the Haskell program language. And I'll be happy to take questions.
if you're defining a function using types in the logical fragment, is that still executable? And two, can you do equivalence of a type defined in the logical fragment when defining the programmatic type?
Yeah, you can use the logical proofs to reason about both fragments. So there's the subsumption property which says if you have a logical program, you can use it within a context that expects something that's programmatic. So in terms of usage, you can use the logical programs anywhere, including executing them at runtime.
I have a question about data types. In languages like Haskell, you could define Russell's paradox using data types. So how does your calculus catch things like this? Do you have to declare data types in the logical fragment and subject them to more rules, or how does that work?
I guess just to clarify, system D, the core calculus is very minimal, so we don't actually have data type definitions. So the details is that our system uses type-in-type axiom to sort of add divergence to the programmatic fragment. And to make the logical fragment terminate, we just exclude the axiom. So like I said earlier, the termination checking mechanism is not part of our work. You can use the existing approaches. So yeah, I think if you were to actually make it into GHC, you need to have some restriction on your data type definition. And another interesting thing that I want to add is there's also a matter of whether the data type is actually inductive or co-inductive, which we don't have a solution yet, but I imagine we'll be asking too much if the user has to write 2 copies of their list data type. So I think that would also be an interesting future research topic.
Cool, thank you.
Yeah.
Okay. Really interesting talk. Thank you. And maybe you partially answered my question already, but I was surprised to see that reflexivity and equality are primitive in your system. What happens if I want to, define my own, say, if I want to do heterogeneous equality, or if I have an inductively defined proposition, do these things get erased as well?
So I guess that kind of, it's kind of similar to the previous question, because when you're defining your new data types, you can specify whether they're actually inductive or if they can encode, for example, Russell's paradox. And I imagine if you have this primitive equality type, you can build on top of it and have other inductive types that make use of it, and then you can erase those as well. But then it's pure speculation at this point, because we don't have inductive types in our language.
Right, I realize. Thank you. Yeah.
Let's go to the other side of the room. Yeah.
So thank you very much for your talk. You showed that proof erasure has an effect on the termination behavior of the program, and but there could also be other types of effects of proof erasure on other parts of the evaluation behavior. For example, if you remove the proofs, it could be that less parts of the data structures are evaluated, because Haskell is a lazy evaluated language. And so I was wondering if you considered these other types of effect on the evaluation behavior.
So I guess here the assumption is that you only erase something when it's actually pure, and pure in the sense that it doesn't even include divergence. So I guess, I'm not sure if the case you're talking about, if it's pure, then it doesn't really matter the order of evaluation, because you're going to end up with the same thing, regardless of the evaluation order. Are you worried about more fine-grained, performance issues?
So performance is one thing, but there could also be out-of-memory errors or stack overflows that do not happen when you erase the proofs, for example.
I guess in that sense, by erasing the proofs, your program becomes more defined, which is not a bad thing, I would say.
Thank you.
I think we've got time for a short question and a short answer.
Okay. So I think you mentioned that inferring coercions was undecidable for the core system DE. Does that mean elaboration would also be undecidable, or is it more restricted from the surface syntax somehow?
So the short answer is no, it's not decidable, because your equality can kind of witness, your equality proof can witness to programs that can potentially diverge, and that is in general not a decidable process. And you can sort of already do that even without dependent types with the undecidable instances. So, yeah, it's not decidable.
Thank you. We're out of time, I'm afraid. So if you didn't get a chance to ask your question, I encourage you to try and find the speaker at lunchtime.
Yeah, we can talk after.
Okay. Thank you. Yes, thank you.